Hi everyone, and welcome to another episode of Mr. Carlson's Lab. Today we're going to talk about solving different types of noise and interference issues. So we're going to take a look at solving radio frequency interference issues, and we're going to take a look at solving electromagnetic interference issues. So each one of them is created by different devices. Some devices create both, and you would be surprised how noisy your workplace and your home is today. I've created a device that we can take a listen to just everyday appliances with, and you can see how much noise they're making all the time when they've been left plugged in. You'd be quite surprised. So whether you're a sound engineer, whether you're an RF engineer, or whether you're just somebody trying to solve noise and electromagnetic or RF interference issues in your home, this will be beneficial for everyone. So let's get started. This is a device that I created some time back, and I released this publicly, quite a while ago. I'll talk a little bit more about this probe here in a little bit, but it's really effective in finding noise issues, whether it be a noisy component inside something you're servicing, or whether it just be noise from a device like I'm going to show you. So what I'm going to do is I'm just going to turn this tablet on. I'll show you how sensitive this is. The probe is not even turned up. You might be able to hear that hum. It's picking up hum from that direction. So anyways, I'm acting as a shield because I'm connected to the ground of the probe here. Anyways, I'll turn this on, and you can see how noisy just a standard everyday device is. I have to turn that down a bit. Let's go to calendar. I'm just pressing random buttons here. So there you have it. That's just a standard everyday device. Look at all the noise that screen is making. So let's take a listen to another device, see how much noise it makes. Here we have a good old-fashioned linear type power supply, and we have a modern switch mode power supply. What's the difference between the two of them? Well, obviously size and weight and noise. So why is a linear power supply so much quieter than a switch mode supply? Well, I'll explain all of that in a moment. Right now, I'm just going to tell you how these things operate. So first of all, the linear power supply is really quite simple. It plugs into the wall. It uses the AC mains to oscillate a transformer in here at 60 cycles. That 60 cycles runs over to some rectification, usually either 2 or 4 diodes. So 2 diodes, depending on the way the secondary is set up, if it has a center tap, or if it doesn't have a center tap, they usually use a full wave bridge rectifier. And then that runs into some capacitive filtering. And sometimes after that, if they want the output voltage regulated, they'll put a linear regulator inside here, and then we have our current supplied at the leads here. So really nothing in here that makes a whole lot of noise. And why this doesn't make a whole lot of noise is because it's driven from a sine wave. This isn't creating any square waves inside here. Square waves are harmonically rich, and that's what these things have inside. And the way that these things are designed and the way that they work is a little bit different than this as well. So we'll talk about that here in just a moment. So let's take a listen to this linear power supply, and then I'll plug this in, and we'll take a listen to this supply. All right, so grab my cord here, move this out of the way. So I'll turn up the probe. Now you're going to hear the AC line making noise, and you'll hear that over this because it's going to be connected to it. So on most AC outlets, when they're wired correctly, the smaller slot is the hot side and the larger slot is the neutral side. So if I bring this close to the hot side of the line cord, because the line cord is flat and it's running in, this is the hot, and this is the neutral. So if I go close to the outlet, so I can tell what side is hot with this probe here just by doing that. Now, I'll put this on the bench. Now this is so sensitive that it's going to probably hear this being plugged in. You'll hear the popping as this is making connection to this. What was that? Making connection. Okay. So again, this is the line cord, or the actual cord running out. This is the line running in, the line cord running out to the device that would be powered, direct current from this device. Again, line cord noisy, right? It's just picking up the hum. So you can see nice and quiet. Nice, quiet. Now these things were known as wall warts way back in the day. So for those of you that aren't familiar with that term, if you hear the term wall wart, that's what these things are. So they're heavy, they've got a big chunk of iron inside, which is known as a, old transformer, and just very, very simple design. And as you can see, nice and quiet. Versus a modern switch mode power supply. It's light, right? And it's, they make lots of current for a small size, but with everything else, there's a trade-off, right? So I'll plug this in. Now I'll bring this close to the cord on this. Now what I'll do is I'll bring this close and I'll unplug it. So there you go. So when I plug this in, you'll hear the power supply basically power up, and then once the load or the lamp that this is attached to turns on, you'll hear the tone change because it's under load. Okay, so here we go. Alright. So you can hear it basically get plugged in. So the bridge rectifier that's on right on the line cord here is powering the circuit up, and then once the supply is furnishing current to the load, it gets really noisy. There it is. Now, your house or your office or whatever you're in is most likely littered with these things. The little power supplies that charge the phone that you use, that are, powering your tablet, that are in your television, that are in your appliances. Most of all of the appliances nowadays have switch mode power supplies in them because they want to keep size small and they want to save on cost because these big transformers cost a lot of money to make. So you can see a trade-off happening here. So why are these so noisy? Well, I'll get a piece of paper here and I'll draw you a block diagram and I'll compare that block diagram to this, and you'll start to understand why these things make so much noise. Effectively, these little things are small transmitters. So what's inside this power supply here? Well, it's really quite simple. So first of all, we have a transformer. I'll draw it the way it looks inside. We have a primary and a secondary side. 2 wires on this side, 2 wires on this side. The electrical symbol for this is this right here. Okay, that's a transformer symbol. So this just plugs right into the wall. So we can call that the plug right there. Okay. This runs out to a bridge rectifier, which is sometimes a square block, sometimes it's 4 diodes, just depending on what they've used. We have the AC side here, and then we have the DC side here. This runs out. We have a filter capacitor here. I'll just draw this as the electrical symbol because it fits between those two, nice and simple. So this is usually with a power supply this size, usually between 2200 and 4700 microfarad. All right. And then if they want to get fancy and have some form of regulation, they'll usually have a linear regulator inside. It looks like this, and then down here, and like this. Usually in a TO220 package, something like that. And one more capacitor here, small one, to keep things nice and stable. And then this is the output, right? So we say this was a fixed regulator of 12 volts. That might be a 7812. Well, here's another little trick for you. Whenever you see 78, that means it's a positive type regulator. If you see 7912, the 79 means it's a negative regulator. 12 means the voltage, so it's 12 volts. So if it's a 7805, right, that would be a 5 volt regulator, positive type. If it's a 7905, it would be a negative regulator, and it would be a negative 5 volts, okay? So very, very simple. Usually this is a small value, 2.2 microfarad, something like that. And sometimes for noise considerations, they'll add a ceramic capacitor across there as well, okay? And this is sometimes just 4 diodes, again, sometimes a square bridge rectifier, and then units are transformer. That's all there is, and this is driven by the AC mains, so it's a nice smooth sine, okay? Coming in here, and we get rectification, and it's virtually a silent circuit. And you'll find this type of topology used in a lot of high-end audio gear and anything where there needs to be, a really, really quiet type circuit involved. Very, very, very simple circuit. So what's inside our little noise-making power supply? Well, there's a lot of circuitry inside here. It's a lot more complex than a linear supply. And it has to be that way in order to reduce its size and to allow this thing to, provide the amount of current that it does for its size. So we have our outlet here. All right, so this plugs into the wall. That runs directly into our bridge rectifier. Same type of bridge rectifier that's in the linear supply. Just draw that as a block again. So that's the output side. There's a filter capacitor. Now in power supply language, this is often known as a bulk capacitor. So you'll hear that term tossed around amongst people that service power supplies. When they say bulk capacitor, they're usually referring to this capacitor right here. So as you can see at this point, it's basically in the plug into a bridge rectifier, which usually consists of 4 diodes. And then we have a filter capacitor here, which is usually a smaller value capacitor. And then of course it has to, be a relatively high voltage capacitor because we have rectified mains here, right? That goes right into an oscillating circuit. So right into this little oscillating circuit. I draw out the entire oscillating circuit for one of these things, but I would be here for 10 minutes drawing it out with all the details, so we'll just draw it as a block to keep things nice and simple. So what this thing does is this takes the nice smooth AC sine wave, we get rectification, and that turns it into a very fast square wave. So a lot of switch mode power supplies will say run in the area of, say, 500 kilohertz. We'll just say 500 kilohertz for argument's sake, okay? So this now controls a FET. All right, I'll just draw this FET here, just very simple. Now this is connected to a transformer. Like the transformer that's in this, but much, much smaller, and it's designed to run at a much faster or much higher frequency. Okay. Now, what happens here is this thing is taking this, 60 cycles, right? Or 60 hertz if you like, and turning that into, say, 500 kilohertz, all right? And that 500 kilohertz is now a square wave. Now, square waves are harmonically rich, and harmonically rich means that we're going to have an RF fire hose, or if you'd like to call it a noise generator, all right? So they try to put as much suppression in these things as possible to keep these things from radiating, but again, we're dealing with a plastic case. There isn't a whole lot of shielding here. Nothing like having a metal case or something like that, right? Now, the reason that they they up the frequency so fast. They take it from, 60 hertz to 500,000 hertz, is because you can down the core size of the transformer. All right. So the faster that you're oscillating this transformer, the faster the frequency it's running at, the smaller the core size gets. Now, it's one of the perks of a switch mode power supply. Now, they're driving the gate of this with a nice, clean, fast square wave. Why are they doing that? Well, because on a sine wave, if you were to look at it on an oscilloscope, it looks like this. All right. So we have a nice gradual rise, and then, it's gradually coming down to the base and changing polarity and then doing that again, right? Right on this side. And then coming up to zero here, sometimes known as zero cross. Now, with this here, because we have a FET here and it's a small switching device, we need to turn this thing on and off as fast as possible to keep this thing out of a resistive region. So if we had a nice gradual turn on like this and a nice gradual turn off, this thing would burn up in no time. Because as this is doing this, you can picture it like a dimmer control in your house. As you're gradually turning the lights on, they're coming on nice and slow. And then when you turn them down again, they go down nice and slow. We don't want that. We want this to act as close to a switch as possible. We want it just to turn on and then to turn off again. So there is no resistive region or linear region that this thing is going to be running or operating in. And that's the reason that we have such fast square waves. Again, dealing with a very quick rise time and a very quick fall time on a square wave like this makes a signal like this very harmonically rich. And of course, at that point, we're going to get a little bit of noise and radiation out of these things. Now on this side, just to continue this, we have another diode here, and then we have some filtering on this side. And then this will usually have another capacitor here that's, smaller value capacitor, usually ceramic and stuff like that, to get rid of some of the noise on the output side, depending on the quality of the supply. And then from here, we have this run down over here to a thing called an opto isolator. And then we have our feedback here, which tells this thing how to regulate so that we get regulated voltage at this. So if it's say a 5 volt, we don't want this to go to 6 volts when there's no load, and then when you load it down to 4 volts, we want this thing to compensate. And the way that this thing compensates is it changes the amount of on time that this FET is seeing. So just say that there was no load, okay, and we were looking at the pulses. The pulses might look like this, right? And then as we start to load the power supply, the pulses will start to look like this. So you'll see that there's more on time here, right? Now, I explain all about this stuff on Patreon. I've gone into designing switch mode power supplies up there, boost supplies and all sorts of things. And a boost supply is basically just another switching type of supply. And it's a simple type of supply where you don't need an expensive transformer. And anyways, I go into all of that up there and I demonstrate how this works. I load them. You can actually see this move on an oscilloscope and things like that. But this is really going beyond the scope of where we're going here. Now, this thing here is an opto isolator. So this is optically isolating the secondary side from the primary side here. The reason that we're doing that is because we can't have any connection between this and the output side for safety reasons. As you can see, even on this one, we don't even have a polarized plug. You can plug this thing in the wall like this, or you can plug it in like this. And on top of that, many houses aren't even wired correctly. I've seen so many miswired houses. So they've reversed them in some houses and things like that, which make things unsafe. So in order to make this thing as safe as possible, we need complete isolation between this side and this side. So we optically isolate the secondary side here from this side, which is the driving side right here. So we have isolation through the transformer, of course, because we have magnetic coupling, really, what's going on here, right? And then here we have just optical coupling. That's what's happening on this side. And that really, in short, is a switch mode power supply. So you can see that this is much, much more complex than something like this. Now, you would think with all the engineering and ingenuity that goes into something like this, this thing would be worth a lot more money. Well, oddly enough, it isn't. So these things, even though they've got all of these complex parts and it takes so much time to design FETs and bridge rectifiers and capacitors and things like that, you'd think a big chunk of iron inside something like this would be so much simpler. The fact is there's so many of these things being pumped out, the price of these things is being driven right down. And that's why everybody's using these things. Again, the downside to small and, current delivering capability for something so small is the fact that this thing is going to give off noise. So now the big question is how do we take the noise down on something like this? How can we actually calm the noise down on a device like this and the devices in your house that are possibly radiating? I'll talk about that here in just a moment. So how do we make something like this nice and quiet? Well, with a power supply like this, it's not that incredibly easy. This thing would need to be completely shielded, and then you would need to have some form of RF filtering on the output side to make things very, very quiet. So basically, how this would work is, I'll just grab another piece of paper here, and this is a very effective way of filtering stuff, works out quite well, is this entire thing would need to be placed inside of an aluminum box or something like that. Now, of course, this is taking, breathing, letting this thing, have some form of airflow. If it gets hot, right, we need to take that into consideration. So some form of a shielded box. So this thing would need to be placed inside of a box. And that box would have to be completely shielded. And then on the input side of the box, we would need some inductors. And we would also need some capacitive filtering here. And on this side, on the output side, we would also need some filtering inductors. And we would need some capacitors here as well. So some capacitors would run to the box and then to here like so. And then at that point, of course, there's no connection here or here. We would have our filtering, but this would be completely shielded at this point. Now, depending on whether the metal box itself is referenced to earth or to your safety ground, if you want to call it that, or earth ground, X and Y rated capacitors, so say X1 and Y2 rated capacitors on the primary side may be able to be used. And then on this side, we would have ceramic bypass capacitors, and sometimes called, decoupling or whatever type of capacitors on this side here. And what that would do is that would take the noise on this side and really keep it down, because we have filtering through inductors on this side and filtering on this side, and the box would completely shield this device. So if you're in the audio industry and say you have a very noisy situation, say you have a power supply that's close by that's needed for a very important piece of equipment, but it's just this noise generator, this very often is a very good solution. Now, depending on how much noise it makes and how strong the noise is, depends on how that particular type of, sometimes it's a cast box or aluminum box, it needs to be sealed, and how the lead out wires from the inductors need to be fed out. So that also is very important, because any type of a hole that you have in the box is a possibility for noise radiation as well. So all of these things need to be, taken into consideration. Now, with a power supply like this, if you're thinking, well, this is pretty extreme for something in my house, how am I going to knock the noise down? Really, with something like this, it's replacing this with something linear. Either that, or you have to go to an extreme, and basically you're taking the cost of this supply and you're upping the cost by adding this shielding around this. But by having this inductor and capacitor network on this side, you're going to deal with a virtually silent output. Like, you're going to basically have a very silent output. And depending on how well it's designed, you can even get it more silent than a linear supply, because a lot of the times you filter some of the crap off the AC line as well, right? So that's really how that's done. Now, opening these things up and making these things quieter, so like say this thing is just excessively noisy, or say you have a switch mode supply on your phone that's excessively noisy, sometimes these can actually be modified, but it's not suggested that you do that unless you really know what you're doing, because you're dealing with something with AC mains. And there's capacitors in here that can hold a charge for quite some time when these things are disconnected. So all of this stuff has to be kept in mind. So, you know, if you're going to be modifying a power supply like this to try and make it quiet, you know, of course you're doing so at your own risk. Be very, very careful. So when you're dealing with a supply like this, things do get kind of complex. Say you have a little device like this, charging your cell phone or powering up a tablet. Just for curiosity's sake, let's take a listen to this. Wow. Actually stays running for quite a while. That capacitor's holding a charge in there. Let's see how long this thing makes noise just sitting here. Wow. And there it is. It stopped. So there you have it. That's what the capacitor's doing in there. It's even after you unplug it, it's generating noise for a long period of time. Wow, that is quite the noisemaker. So, at any rate, well, that was interesting. So, in order to make something like this a little quieter and to, you know, stop this from possibly interfering with a very sensitive device around it, again, this could be placed inside of a shielded box. And then the USB cable that comes out of this side, they're usually shielded themselves. And if you had this inside of a metal box and you somehow took the shielding of that and connected it to the metal box, so this would be completely isolated from everything. The only thing that would be connected to the metal box would be the shielding of the USB cable. You could probably quieten this down a little bit. Again, you'd probably need some bypass capacitors from this to the box on the output side here, something like that. Again, it's tricky, you know, trying to get the noise out of this. If you're an RF engineer and you've been dealing with this stuff like I have for a very long time, chances are you know my frustration with these devices. So any type of sensitive radio or anything that's around these things, you know, they can really pose a problem. Don't even get me started on the older plasma televisions. Boy, I'm glad that time is done. Whoa, those things were noisy. Those things would transmit from houses away. You could have an antenna outside, and I'm telling you, houses away, 3-4 houses away, you can listen to your neighbor's plasma set. And, you know, as the scene is changing on the screen, you can almost tell what he's watching, or him or her is watching. So, again, yeah, another little noisemaker, and they're all like that, and they're all emitting some form of noise at some particular level. Now, let's talk about a different device and how to prevent noise from getting into it, and how noise can get into devices. A lot of the time, RF engineers and audio engineers will come to the point where they realize that they just can't solve the issue at the transmitting end. So at that point, it's time to try and solve the issue on the receiving end. So it's time to try and get that radio signal or interference out of whatever's receiving it. So for example, say a microphone is receiving some RF or something like that. There's something that always has to be kept in mind. It's a microphone. It's not a radio receiver. Why is it receiving radio signals in the first place? So, for example, say you have a microphone. Okay, so we'll draw a microphone like this. Pardon my horrible drawing. So this is a metal-cased microphone, all right, like this. So it's basically a solid metal case. So for example, here, I'll grab one of these. Here, I have this off to the side. So it's a microphone like this, okay? And as you can see, it has a metal body on it, and it's very well shielded. So the entire case is shielded, and so is the grill on the top. I mean, no RF is getting in here, right? There's no plastic parts on this, so it's completely shielded. So that's this microphone right here. So these microphones here have a vacuum tube in them, so there's a preamp in them. There's a box that has to supply power to this mic, so we have a cable that runs from the power supply. There's a cable that runs to a wall outlet here. And then we have usually a cable that'll run off to some processing gear, a mic preamp, or something like that. So we already know that this thing is, a solid metal object. And since we have a shielded cable that's running to it, it's usually connected to the shell. So this is completely shielded to this point. So we can almost say that, no RF is really going to enter this unless, we're dealing with a resonant length and a really powerful radio transmitter or something like that. And, we're dealing with some extreme situation, right? Now, if we go to this side of the box, we can see that we have a power cable here. And much of the times, this is just a standard 3-wire power cable, something like you'd find on a computer power supply or something like that. Well, this isn't shielded at all. So RF interference can get in through the cable, get into the microphone itself, get amplified by the amplifier in the mic, and then sent back out into the processing gear. So a lot of the times decoupling is actually needed at this point right here. Now, some of you might be saying, well, I have a fully shielded cable that runs right to the outlet. Well, that's all fine and dandy, but this plugs into a wall. And if it's in a building or somewhere, there's probably miles of open 14-2 behind that wall where RF can get into. So there's a really good chance if there's a resonant length of wire in there or something like that, it's acting as an antenna, it'll put the received signal right into the box. So there has to be proper decoupling added into the actual box. Now, depending on who makes the mic and who makes the, the power supply and everything, there might be some decoupling in there, but maybe it's not enough or maybe it needs to be tweaked. So now, as you can see here, we have a cable running up here. So this has got to supply a DC filament, right, which is usually about 6 volts or something like that. Up here, it has to supply the B+, which is the, the plate voltage for the tubes. And then we have an audio signal that's coming back down another wire out of here, and that usually just goes through this connector over to here and then into this connector. So here, because we have a break, usually this will solder to a circuit board, or there'll be open connections in here on the connections. Actually on the connectors. So we'll have some breaks in this, and then it'll come over here and we'll have another break where it might go into a printed circuit board and then some exposed wires up to here. If there's any RF getting in here, there's very easily get into that open unshielded area. So you can see there's issues that can, crop up in all sorts of different designs, and all of these things have to be looked at. So basically you're looking at, bypass capacitors, decoupling capacitors here, and you'd be looking at, possibly adding better shielding over here, or sometimes even lifting the wires off a circuit board and then running them directly from side to side, things like that. There are all sorts of ways to fix these issues. Another thing that would tell you this is that, say you have another microphone of a different brand, and say it's over here, right, and you have your other microphone over here, and you have plugged in over here, and say you swap the XLRs around, they're both plugged into the same outlet, and you swap the XLRs into the same jack. This mic is receiving the RF interference and this one isn't. Well, what does that tell you? Obviously there's going to be a leak in here somewhere. If one mic is going to be receiving the problem and the other one isn't, obviously it's not going to be too big of a deal to solve, right? It might be an invasive procedure. You might have to go into the mic and add decoupling caps in here or something like that. The thing that you do is you go everywhere except the audio line. The audio line is always the last place you go to add decoupling or any type of filtering, because you want to leave that audio line alone as much as possible. So you're looking at the AC line that plugs into the wall, and any breaks in here and things like that you'd be looking for in the shielding, things like that. And again, very last case scenario, you're going to be adding decoupling. And there are some tricks that would basically not even affect the audio as well. So, and it has to do with adding inductors in line and things like that. And I'll get more into that in the future. This is really going beyond the scope of this video. But at any rate, there's always a solution to this type of an issue. So this is really common. Here's another example between ham radio operators or CB radio operators and people with just televisions and things like that. So way back in the day, televisions used to have tuners inside them, and they're not like now where, you plug them directly into your internet and everything like that. So they have a tuner that connects to a Cablevision wire, and that would run out. And ham radio operators would, be talking on the radio, and say 2 houses down, the neighbor is receiving them on their television. Well, a lot of the times the neighbor would immediately think that it's the ham operator or the CB operator's fault because they're coming through their television. Well, a lot of the times, not all the time, but a lot of the times, ham radio operators are operating within their guidelines, and same with the citizen span operators. And what ends up happening is the television on the receiving end is actually the issue. The television manufacturer didn't put enough shielding in the television, and the television itself is a broadband receiver. So any stray RF that's around it will get detected by the TV and, put out the speakers and maybe get a wavy screen. Now, way back when I used to help people solve their RF issues, especially in the amateur radio world, I would get calls and saying, hey, I have some interference issues. Could you come and help me with this? And I would say, sure, And I would talk to the neighbor, and I'd look at their television, get the ham radio operator to transmit, and sure enough, their television screen would be all like this when he transmitted, and as soon as he stopped transmitting, everything would clear right up again. So I had a really good television that I just used for this purpose, and it had really good shielding in it. And I said, well, let's try this out. So I would put the television, my television, right beside their television, and I would tee the Cablevision lines, and I would plug both plugs into the same outlet. And I would tell the amateur radio operator to start transmitting again. And he would do that. My television would not move. No sound out of the speakers, picture remained solid. Their television, wavy screen, all sorts of things. And I'd say, so what do you think that is? Right? Because the ham radio operator is operating within his guidelines, right? So the owner would say, oh, well, it looks like it's my television. And I'd say, exactly. So then what I would do is I would help the owner, and I would usually install decoupling caps and RF bypass and stuff in their television. We'd fix the problem, and we'd have 2 happy parties. So, and that would just show the person on the other end that, it wasn't always the amateur radio operator's fault, because a lot of the people that owned the televisions that did get wavy screens and things like that, they would be absolutely irate. And I'm telling you, irate, like unreasonable irate. And just that quick example calmed them right down. A lot of it worked so well. And then, of course, after that, we would end up, because they would cooperate after that, we would, go about repairing the issue. Right? Just add a few capacitors is usually all it was. Really, that's all it was. And a lot of the time it was across the line cord. And that was just it. So XY rated capacitors and a 3-prong plug thing like that would be just absolutely fine. So there you have it. Now, for those of you that are interested in trying to troubleshoot this stuff, say you have problems with, say you're an audio engineer or an RF engineer, and you're having problems finding issues in a system like this, I've developed something that's opposite of the super probe. This actually will insert signals into cables. So you can run this along cables, and if there's any leaks in the cable, this will help you find it. So this is called the Carlson non-contact signal injection probe. Okay, so I'll give you an example. Here's a super probe. So this is the receiver. I'll put this in the RF position right now. All right. And I'll turn this on. Hopefully that's not going to be too loud. I'll turn this on. So you can see, this would be very, very useful for finding any types of leaks in cables and things like that. So, for example, here, I'll just turn this up just a little bit. So this is in the RF detection right now, okay? So where we had this before was here, so that you could hear all the frequencies. You could hear the hum, you could hear everything. I had this in here. You can see I have to get much, much closer. Whereas if this is in the RF detection mode, right? You hear how strong that is now? Because now this is designed to actually look for RF issues. All right. So this is an RF signal. It's coming out of here, and it's modulated. So as you can see, I'll just turn that back here, right? So that's off. And then this is just an RF signal. You can see the LED is lit, but there's no sound, right? All right. So not modulated and modulated. And of course you can vary the signal level. If I turn this here, you'll hear it without that kind of squelching effect. So very, very useful for finding issues with interference in microphones and cables and all sorts of things like that. This thing is always in my toolkit, and I use this thing a lot. In fact, the Super Probe is incredibly beaten up because this thing has been rolling around in my toolkit so much. So these are two devices that I use a lot. I'll just shut that off. Two devices that I use a lot. So this has been publicly released on YouTube. You can find the video. Just look up Carlson Super Probe and all the plans are there to build it. If you want the actual original circuit board designs and a lot of other literature on this, that's all up on Patreon. So that's some files that are up there. And the entire build file for this, printed circuit board layouts, alignment procedure, all the notes and everything that I've recorded when I designed this device, it's all up there as well if you want to build one of these things. So if you're an RF tech or an audio tech, this is an indispensable tool in the audio industry for sure. And of course, if you're wanting to look for noise and problems like that in devices, this is indispensable. Two very, very useful projects. So definitely check those out. I plan on putting out a video where I'm going to actually install decoupling capacitors, and I'm going to show you their effect on the actual circuit and their effect on the audio as well. So I have lots of interesting things coming, as well as this microphone that I showed you. It's a great microphone. They're great right out of the box. But I'm going to redesign this, and I'm going to share this design with you as well right here on YouTube. Share the whole procedure. So I've got a pretty neat idea for this thing coming up. Again, it's a fantastic mic the way it is, but I think I can improve it. If you're enjoying my videos, you can let me know by giving me a big thumbs up and hang around. There'll be more videos like this coming in the near future. We'll be taking a look at all sorts of different electronic devices. If you're interested in understanding how they work, this is the place you want to be. So if you haven't subscribed, now would be a good time to do that as well. If you're interested in taking your electronics knowledge to the next level and learning electronics in a very different and effective way and gaining access to many of my personal electronic inventions and designs, some of which you've seen in this video, you're definitely going to want to check out my ongoing electronics course on Patreon. I'll put the link just under the Show More tab below the description of this video, and I'll also pin the link at the top of the comments section. So if you click on the link, it'll take you right there. All right, until next time, take care. Bye for now.